we're looking for patterns that are compressing. Well, these two are, right? But if we look at correlation-based measures of similarity, you'll find that they couldn't actually be more different in a mathematical sense. Their correlation, and I'm running that right now in a Pearson product moment sense, is -1. So this measure of similarity is not going to be useful to us. Also, if we're comparing a short pattern to a long pattern that is identical, right? It's just stretched in time. We wouldn't be able to do that using correlation because they're not the same length. You can't compare the two. Also, we need a method that is flexible, right? That says, look, we're looking for patterns from the right. We're interested in what's going on now in terms of a pattern match, not what has been. So you see where my highlighter is. This is old news. We don't care about that. So we need to be able to search for patterns from the right. So, and at the end of so keep in your mind's eye here what these look like. The chart batch that we create will look like this. So this one was the highest match, Zimmer. And then you go down, they're not all perfect, right? But you can see the compressing nature of what it's finding. Let's go to the bottom of our chart book. Look at this. So these are not good matches, right? So as we get further and further down, we find things that are not good matches. So we're only interested in the ones in our chart book that are, so this is sorted by degree of match in a dynamic time warping sense. So we have these all sorted. So if we want things that are contracting, we look at the top of our chart book. If we want things that are seriously trending in some direction, we'll go to the bottom of our chart book, right? Because that's the opposite of contracting, would be expanding or trending. And we could search for anything. This is just one particular circumstance, market circumstance that we're showing. So this is the motivation for using something like this. Let me close that. And here we go. Bear with me. Let's look at some of the code. How do we do this? Well, we use R. We have, so tidyquant is a big one that we use, and DTW. We will import some metadata here. We'll filter some of the stocks that we're looking at. We'll import our prototypes, so the ones that we just showed you from a CSV, though not from the exact Excel spreadsheet that I showed you, but literally just the time series of what was used to create those charts. We'll get the data. Notice we're going back 42 days. You could go back any amount of time. In fact, the chart patterns that we're showing, that we're matching to, are only 8 units long, right? But it doesn't matter. Remember, we're harnessing the fractal nature of what dynamic time warping can do. That's so cool about that. And we don't need to worry about how long it is. We don't need the guarantee that the sequences are the same length. It doesn't even matter. So what is dynamic time warping? So what are we doing here? The way it works is let's go to, this is a really good example. Here's a grid. Okay, so on the y-axis is the index of all the points here. This is just one example, 2 strings. And the x-axis is that other array, right here, x. And basically what we look at is we compare all pairwise points and then compute their Euclidean distance, which is the difference between the 2 points' values, squared. And so what dynamic time warping does is we enumerate all those possibilities, right? But we don't have to, and then we figure out how to align the 2 sequences with minimal cost, meaning the sum of their differences, square differences, is minimal. So that's a tough problem, right? And what we do is we build what's called an accumulated cost matrix, and we travel through it, comparing adjacent points. Now we can impose restrictions on them. First of all, we're going forward in time always. We're never going backwards in time because that's not that doesn't make sense. And we're either I should say we put some really important constraints. Like, for example, we could put a constraint that says, look, we don't want jumps to be in our warping path. So we're never going to be interested in, say, 0.16 here. Okay. We want to stay along sort of a smooth trajectory from the bottom left to the top right. The closer it is to that kind of trajectory, the closer we are to kind of just comparing each point in time sequentially. But we do allow some jumps, right? So we want to put some constraints on that. And that's where these concepts of warping windows and step patterns come into play. You'll see that those are arguments in the code. It's pretty cool stuff. And I'm not terribly sure about how every different type of dynamic time warping algorithm works. So I build a loop that gets computes these dynamic time warping distances for all the different methods that are used. And then what I do is I look at the median value and say, okay, fine. If security is ranked well by this algorithm across a bunch of them, a bunch of different algorithms, then maybe it's going to give me a good match. So then I sort the securities that way based on their median value across a number of different dynamic time warping algorithms or their parameters. So the other thing. So the reason why this is not combinatorially explosive is because we don't have to recompute these values. So each of these values here is the squared difference between the distances for each. They are effectively a Euclidean distance of 2 points in those between a pattern sequence and a pattern prototype sequence and a test sequence. So it's not combinatorially explosive because we don't have to recheck these points. Like I don't ever have to check 2-1. I don't have to check 3-1 if I've already determined that we're optimal up to this point. So that's why it's called dynamic, because it uses a concept from dynamic programming, which is that the problem contains optimal substructure. Optimal substructure is a key thing that allows us to do this efficiently and not have to recompute points. This is called an accumulated cost matrix because what we're doing is we're doing the sum of squared differences between points, and then we're keeping a record of what that sum was at every point. And then taking that plus the next difference, plus the next difference, plus the next difference, plus the next difference, plus the next difference. You can see when we're going up, that's taking, the concept there is that we're using a one-to-many relationship. So we're comparing 0.45 also to 0.46. So we're comparing the same point in one series to the other series twice. And you can do that in dynamic time warping. It's pretty cool stuff. So let's go back to the code that shows how to do that. Here we're just tidying up the data from Yahoo Finance, tidying up the data. Here we chop it off to the last. So I grabbed 42 data points, but then I chopped it off to the last 24. That's okay. We have to do some more, just in order to use the package DTW, we have to do some more finagling, turn the data into rows. So I do a big transpose here. And here's where I loop through a bunch of different instances of the DTW algorithm, and basically we get our results down here. Let's we created a chart batch. I also have the 100 best ranked security. So I could actually, for Street Smart Edge users, we could do this. We could just copy this and then go into Street Smart Edge and add our symbols, and we can have a watch list. Boom, pretty nice. It also creates the chart batch that I showed you earlier, which had some pretty good matches. So this is it's a useful tool. Reach out to me if you have questions about the code, about how to create a chart batch. You'll notice there was some metadata on the chart batch. That metadata came from another file. We had 3,000 securities or so here. And just different proprietary data that we use and can overlay on the chart. You can do that pretty efficiently. And I'll put some of the code in the presentation so you can just get a better handle of the capabilities that exist in R, and in using tools in R like tidyquant, DTW.